Okay, so for today's notes, we're really focusing on the application of the instantaneous rate of change rather than just finding it from a function like we were doing last week. So big questions for today. What is the difference between an average rate of change and an instantaneous rate of change? And you could certainly write this out on your own notes or whatever, but I think the biggest difference between them is the average rate of change is the slope of the secant line, whereas instantaneous rate of change is the slope of the tangent line. And this is all to a curve, so whatever function you're given, that's the slope of the line that we're talking about. And then for the finding the average rate of change, it's just like finding slope for any old line. So you take 2 points and you essentially calculate their slope. Instantaneous rate of change requires you to find the derivative. So remember, that would be where you're using that limit notation as h approaches 0, and you're finding f of x plus h minus f of x all over h. So today we're going to not only find this derivative, but then apply it to answer a couple of questions. So there's only going to be one example. I tried to make it short for you guys. I know that the AP Bio test was exhausting, so we're gonna try and make this short. I think that you will probably get it after just one pass, and then if you look at your homework too, it's just like 2 of these kinds of questions, and then 2 little spiral questions. So I think that we should be okay in terms of workload after the test. So if we're looking at this question, it says that we have a ball that's thrown up from the ground with an initial velocity of 96 feet per second, and it gives you the function, which is nice so that you don't have to create it yourself, which you certainly could do. And the question's asking us for the instantaneous velocity. So remember, velocity was a rate of change. So really what this is asking us for is the instantaneous rate of change after 4 seconds. Well, in order to find that, we first must find the derivative. So that means, remember, we denoted it f prime of x. Since this function was s of t, I would denote it s prime of t. So this is how we would start finding that derivative. We would set it up with negative 16. We could do x plus h or t plus h. Like I said, I don't like using t's, so I'm going to go ahead and use x's just because I think that my t's start to look like plus signs. So remember, plugging that x plus h everywhere you see a variable, and then we would subtract off negative 16x squared plus 96x. I am putting this in parentheses again to remind myself to distribute that negative, and this is all over h. So I'm going to go ahead and distribute that negative now, which would give me a plus 16x squared and a minus 96x, and then I don't have to worry about distributing it. Okay, I'm going to go ahead and pause the video while I do all the math for this. I would hope that you would do this on your own too. So you can pause the video now, and then as soon as you are done, hit play, and you'll be able to see all the work for the correct answer. Okay, so if you need to pause the video again, you'd be able to go through all of the work and make sure yours matches. At this point, I think this is where a lot of us get confused on notation, so just a notation note. After you've done the difference quotient, you should end up with something that still may have an h in it. So remember, we are taking the limit as h approaches 0 of all of this stuff. So negative 32x minus 16h plus 96. And this is where you could essentially say, okay, the h is approaching 0, so this limit equals negative 32x plus 96. And then this is where you could say the derivative s prime of, we'll call it x since we changed our variable to x, is negative 32x plus 96. So again, after you've done the difference quotient, that's when you show the limit notation. Once you've taken the limit, there's no need to show it anymore. This would be our final answer for the instantaneous velocity at any point. So part A asks us for this instantaneous velocity after 4 seconds. That just means we plug in a 4 for our time. So for part A, we would just do negative 32 times 4 plus 96 I'm getting negative 32 for that, which would mean that the velocity at this point is negative 32. So if you like think about a ball in the air, it would be going downhill because the slope of that tangent line is negative 32. So for example, if this is the path of our, here's our ball that we threw, if this is the path of our ball, after 4 seconds, it's already approaching the ground because here's our time of 4 seconds. Our slope of our tangent line is negative, so it tells us that that ball must be going down. For part B, the question asked us when it hits the ground. So I think for us, we would have to think about this in a coordinate plane. What we're interested in is this point on the ground. So I don't know right away when this ball hits the ground. You could do that a couple of different ways. You could graph the function, the original function we were given, which was negative 16t squared plus 96t. I think I better double check that. Yeah, that's right. So you could graph this in your graphing calculator. It would give you that parabola, and you would be able to do second calc 0 to figure out after how many seconds it's hitting the ground. You could also just factor this and solve it. Essentially, we're looking for where this function is equal to 0, and I think we're all good enough at solving quadratics that we could answer this. So here we can factor out a t. We're left with negative 16t plus 96. So if we use the zero product property, it hits the ground at t equals 0 seconds, which makes sense since it started from the ground. And then also wherever this factor is equal to 0. So we get negative 16t equals negative 96. When we divide those two, we get that time is 6 seconds. So after 6 seconds, this ball has hit the ground. So we had to figure out where it hit the ground before we could answer part B. So now we can answer part B, which asked us essentially to plug in 6 into our velocity equation, which is our derivative. So negative 32 times 6 plus 96. I'm getting a negative 96 here, which means when the ball hit the ground, the slope of that tangent line, so this line right here, sorry, that's a bad line, its slope would be negative 96. So the velocity there would be negative 96 meters per second. Sorry, I didn't label that on my last question. I should have done that. I'll go back and do it so I don't feel guilty about it. Meters per second. Oh shoot, this was in feet. So feet per second. My bad. I'm a bad reader. You know this about me. Feet per second. Okay, so then we can deal with the last part of this question, which was written in for us. What is the highest point the ball will reach? You can do this again using your calculator. If you graph the original function, this is modeling the path of the ball. So you could do second calc max and figure out what that vertex point is. We're looking for the height, so we want to know the y value at that vertex. Like what's the tallest it's going to reach. You could also just do vertex formula for the quadratic that was originally given to us. That is negative b over 2a. So this would be negative 96 over negative 32 if I'm using my b value of 96 and an a value of negative 16. When you divide those two, you simply just get 3, which means at an x value of 3, we reached our maximum height. So to figure out what that height is, we just plug in a 3 into the original equation. So since we're looking for a position and not a velocity, we would use the original equation. And you could use your calculator for this as well. And I'm getting 144. So 144 feet would be the tallest point or the maximum height that the ball would reach. So again, I think that the biggest distinction here we need to make is that we would use this function if we're looking for a position. So if we're looking for height, essentially. Whereas we would use the derivative that we found, we would use this if we're looking for a velocity or a rate of change, an instantaneous rate of change. So that's the distinction to make. If it's asking you different types of questions, you should be able to decide which is appropriate and when. Good luck with your homework!